All right, welcome back to another episode of Science with Surbeck. Today we're going to talk about section 8.1, which deals with forming chemical bonds. The objectives of this lesson is to define a chemical bond, relate the chemical bond formation to electron configuration, and describe the formation of positive and negative ions. So before we get going into too much detail, we're going to outline in general the definition of a chemical bond. And it's simply just a force that holds two or sometimes more atoms together. Now, overall, what's happening is that an atom is attracted to another atom because of those positive and negative items that are in every single atom. Okay? So in our case of our atom, there is a positive nucleus from those protons, and they're attracted to another atom's negative electrons. Again, opposites attract, just like in magnets, and so positive nucleus, the proton of one atom, is attracted to the negative electron of another atom. Okay? So what happens here is that when we form this chemical bonds, we can actually do it in two ways. One, we can have this attraction between the positive and negative, or the positive nucleus and the negative electrons, or we can form ions where all of a sudden electrons are exchanged, either gained or lost, and an atom now has a positive or negative charge, and we call that an ion. And so what we'll talk about specifically throughout this entire chapter is ionic bonds. But again, in general, we have this idea here of forming a chemical bond. We are attracting the positive nucleus with the negative electrons of different atoms. What we also have to do is we have to take a look back at our periodic trends, and we have to notice this. Two things we talked about right at the end of chapter 6, and that was ionization energy and electron affinity. One, ionization energy was saying how much energy does it take to take an electron away or lose an electron? And electron affinity was saying, hey, how much does a atom want an electron, or what's that attraction for that electrons? Now, what we need to know here about noble gases and the role they play in chemical bonding is that they have a high ionization energy and a low electron affinity. So what that means is it's going to cost a lot of energy to take away an electron from a noble gas, and it's going to have a low electron affinity, which means it does not want any more electrons. A noble gas is satisfied with 8 electrons because it fills the outer s and p orbitals. Okay? Because of these two properties, noble gases do not want to gain or lose any more electrons because they have a complete octet, or a full set of 8 electrons. And overall, because of these things, noble gases are non-reactive or lack the chemical reactivity. Okay? Now, the reason that elements are going to react is because they want to gain that full set of 8 electrons and be like the cool kids club of the noble gases and have a full set of electrons in their outer energy levels. Now, again, this happens right here because atoms want to be like the noble gases, and they want to be like the noble gases, and they want to gain that full set of 8 electrons. Now, there's a couple exceptions to that 8 octet rule, and we'll talk about them here throughout this particular chapter. So now, we talked about here in detail, elements want to gain or lose electrons to be like the noble gases or have a full set of 8 electrons in their outer energy level. Let's break it down. And talk about this. Cations. Cations are a unique type of ion, and they have a positive charge. So all they are positively charged ions. Now, with cations, they are going to lose valence electrons to attain noble gas configuration. So if you think about this, a cation, if it loses an electron, it's essentially minus a negative charge, okay? So what happens here is this. It will lose those electrons, so it subtracts a negatively charged electron to become positively charged. And again, we're gaining and losing electrons to get to that full set of 8 or a full octet of valence electrons. All right. Now we have an example here that talks about the electron or the cation of sodium. So we have neon and sodium. What sodium will do in the sodium ion is that it will be like the closest noble gas. So when we get to our electron configuration of the positive 1 sodium cation, what happens essentially is this. We lose that outer valence electron, and I'm going to write the symbol Na and then plus. The Na plus electron configuration will look exactly the same as neon. Now this is dealing with electrons. So how do we distinguish sodium from neon? Well, remember, each and every element has a unique number of protons, and sodium here is still sodium because sodium has 11 protons, whereas neon has 10 protons. So the proton number is that unique identifier for a particular element. All right, let's go on and let's talk a little bit about transition metals and this concept we get with pseudo-noble gas configurations. So with pseudo-noble gas configuration is the stable electron configurations obtained by transition metals. Remember back to our business we talked about with our electron configuration, and we talked about our transition metals, and we said the energy level is the period number minus 1 rho. And it has to do with the d orbitals, the way they're shaped, and some other things that factor into why they are that previous energy level. But what happens here is they're satisfied not with getting 8 electrons, but as long as they obtain this certain number, and it varies from each and every particular atom, but it will always vary a little bit with the d electrons. They're a little bit tricky, and we'll talk about that when we get to naming. So our examples here is zinc and silver. So when zinc and silver form a electron configuration that matches or is as close to the noble gases, what they do is this. Zinc, what will happen here is zinc will lose 2 electrons, and so zinc, whenever we run into zinc, it's always going to be Zn 2+, and whenever we run into silver, it's going to be Ag 1+. And something to note here is that when we have a 1, we assume that it's there. So if you just see a plus, or in some cases a minus, that is saying 1+ or 1-. Okay? Now, moving on here to anions. Anions, on the other hand, are the negatively charged ions. So to be negatively charged, an atom gained electrons. Remember, plus a negative electron to attain that noble gas configuration. So for our example here, we have our chloride anion. And so what it tries to do, or what the atom tries to do, is it tries to match that electron configuration of our particular of our particular element here, or our noble gas. And so chlorine has this electron configuration. It's one away from argon, so it gains an extra electron. And also, when it becomes an anion, a negatively charged ion, it's going to get an IDE ending. So instead of having chlorine, we have chloride. Now, with our parts of the periodic table, our nonmetals are going to tend to gain electrons and become negatively charged. So that brings us to, how do we determine the charge of a particular anion or cation? So we start out with this, all right? We're going to go back a little bit and talk about our valence electrons, because we want to know that for anions, elements are going to gain the number of electrons to get to that value of 8, or to fill their outer s and p orbitals. The charge is equal to the number of electrons gained. So let's check out a few examples. We bring out our number of valence electrons. And that first example here is phosphorus. So I find P for phosphorus, and it has 5 valence electrons. And I ask myself, well, is it easier to gain 3 electrons or lose 5 to get to that noble gas configuration? Well, the answer for phosphorus is, hey, gain 3. So our answer here for phosphorus, when it becomes an anion, it gains 3 electrons. And so when phosphorus gains 3 electrons, it becomes negatively charged, and it has a 3- charge. So phosphorus, when it gains 3 electrons, it'd be written as P 3-. And that minus here indicates the charge of the anion. Again, the 3- here is the charge. That's the charge of the ion. Now, oxygen, we're going to try this in a similar way. So oxygen, we're going to look here. Oxygen's here at the group with 6 valence electrons, and we ask ourselves, okay, do we want to gain 2 electrons or lose 6 electrons to get to 8? Well, the answer is, hey, let's gain 2. Let's make life easy. So oxygen here, what it does is it gains 2 electrons. And when oxygen gains 2 electrons, it becomes an anion with a 2- charge. And again, that 2-, that is the charge of the ion. Now, what I want to show you is this. To determine the charge of our representative or our main group elements, all we have to do is we look at the group. So I'm going to grab a new periodic table, and this is our charge of our ions from our representative or main group elements. So our last thing here that we're going to do here is this. This periodic table, this is going to be the charge of ions, and it's only going to be the charge of ions in that main group. Okay, so we're going to skip over the transition metals for right now. So group 1, anything in group 1 is going to lose 1 valence electron, and when it loses 1 valence electron, it's going to form a positive 1 charge. Now group 2, they will lose 2 valence electrons, so they'll form a positive 2 charge. Now, we skip over the transition metals. We'll talk about that with our naming and formula writing, and we get to group 3. So group 3, has 3 valence electrons. It loses 3 valence electrons to be positively 3 charged. Now, when we get to the group 4, we're at that peak point, and so there's 4 valence electrons. Anything in group 4, or excuse me, this group with carbon can either lose or gain plus or minus 4. Now, nitrogen has 5 valence electrons. That whole group, it will gain 3 valence electrons. So gaining 3 valence electrons, anything in this group will have a negative 3 charge. Oxygen's group, it has 6 valence electrons. To become an ion, it gains 2. So it forms a negative 2 charge. Fluorine's group has 1 valence electron. To gain 1 electron, that it completes its octet. So it ends up with our negative 1. Now again, this is our charges of ions in our main group elements. Notice here the noble gases do not have a charge because they already have a full octet. They're not going to gain or lose those electrons. This is also only for your representative elements. We're skipping over, for right now, the main group or the transition elements. All right, so we talked a lot about formation of a chemical bond. I hope you have enjoyed this particular episode. And if you haven't done so already, make sure you subscribe.